The fourth one is one of the harder ones to explain. We're told that the volume of the container is doubled. We have to, first of all, in this situation, remember some grade 11 chemistry. There are gases involved in our reaction. So if we increase volume of the container, grade 11 chemistry, you might recall Boyle's law, the relationship between volume and pressure of a gas are inversely proportional. So increasing the volume lowers the pressure in the container. Okay, so what we're going to do is talk about pressure instead of volume. Therefore, the system tries to raise the pressure. Now, how could the system raise pressure? Well, on the left side of our equation, we have two SO3s. So on the left side of our equation, there's 2 moles of gas. On the right side of the equation, there's 2 SO2s and 1 O2. So on the right side of our equation, there were 3 moles of gas. The system is going to try to raise pressure by making more gas. So since our reaction has 2 moles of gas in equilibrium with 3 moles of gas, that's 2 SO3s on the left and 2 SO2s and 1 O2, 3 moles of gas on the right, the system is going to shift forwards to make more gas. Okay, 2 moles becoming 3 moles will increase the amount of gas. So shifting forwards, we get more O2 produced. Now again, this was simplified because there were no liquids or solids in the reaction. If there were liquids or solids, you would ignore them. Okay, we're looking simply at the number of moles of gas on both sides of the equation. Now if you're thinking about that, you might be wondering, what if the number of moles of gas were the same on each side of the equation? Suppose there had been 2 moles on the left and 2 moles on the right. Well, in that situation, although the system would like to raise pressure by shifting, it couldn't. It couldn't raise pressure by shifting because there's no difference in the number of moles from the left to the right. So there would be no shift and therefore no change in the oxygen. Okay, so if there's the same number of moles of gas on each side, changing the volume of the container actually has no effect on the equilibrium. The fifth example, this one should be a little bit easier. We're removing SO2. So this is very similar reasoning to the answer to part A. It's just backwards. So if we're removing SO2, the system will try to make more SO2, and I look back and SO2 is a product in this equation, so it will shift forwards, and look at that, we again get more O2 produced. Now again, let me say if SO2 here had been a liquid or a solid, then removing SO2 would have had no effect on the equilibrium, because adding or removing a liquid or adding or removing a solid does nothing to the concentration of that substance. Solids and liquids have constant concentrations. You could also argue that they're not in the equilibrium expression, so adding or removing solids and liquids has no effect on equilibrium.